Excellent. Welcome. Today is April 26th, 2017, and this is the Introduction to Wind Engineering seminar. This is the first in a series of Natural Hazards Engineering 101 webinars, which will provide background for students, faculty, and professionals interested in hazards research. This series explores the effects of natural hazards on the built environment in a broad overview. Introduction to Wind Engineering will be followed by introductions to tsunami and earthquake engineering in upcoming months. For more information, visit the NHERI website at designsafe-ci.org, where you can find links to the SimCenter and NHERI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructures Simulation and Computational Modeling Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily reflect the views of the National Science Foundation. Today we welcome Professor Gurley from the University of Florida. We are pleased to have him open this Natural Hazards Engineering 101 seminar series with the Introduction to Wind Engineering. Professor Gurley is a co-PI of the University of Florida's NHERI equipment facility, which includes 5 wind hazard research instruments, including a large reconfigurable boundary layer wind tunnel. His primary areas of research are the wind effects on residential structures and stochastic modeling of ground level hurricane winds and wind loads on occupied coastal residential structures. Dr. Gurley received his master's and PhD from the University of Notre Dame in civil engineering and a bachelor's of science from the University of Illinois, Urbana-Champaign in aeronautical and astronautical engineering. Dr. Gurley is an associate editor for the ASCE Journal of Structural Engineering and the associate director of the University of Florida's Engineering School for Sustainable Infrastructure and the Environment. Professor Gurley, welcome, and I invite you to begin.
There we go. All right, you can hear me?
Yes.
Okay, thank you. Thanks everyone for joining me. It's an honor to be the kickoff speaker for this series. An acknowledgement to the organizers at the Computational Modeling and Simulation Center, and of course the sponsors, the National Science Foundation. I want to acknowledge, to start with, a whole bunch of contributors. The slide deck that I'll go through today has been pulled from many different resources from many different universities and instructors and people in industry. So a bunch of people by name on the slide, and of course the pioneers that preceded us gave us some shoulders to stand on. We're greatly appreciative of. I wanted to begin with just a quick view of, some of you may or may not be aware of, the number of different experimental facilities available through the NSF NHERI program. The 2 that I'll be focusing on, or the material I'll be covering today, are most appropriate for the ones with the blue box around them at the University of Florida and Florida International, who both have wind hazard facilities. Other NHERI entities include the Computational Modeling and Simulation Center, the Network Coordinating Office, and the Cyber Infrastructure Group, which produces the Design Safe website, which has been sending you the notifications. All right, so the contents for today, I'll start by saying I recognize that the target audience, from my perspective, are people who don't necessarily have any sort of a background specifically in wind engineering, haven't taken a course in wind engineering necessarily, but are probably engineers, some of you students, I would hope. So with that in mind, and also knowing that this is being recorded and that you can download it or view it at some other time at your leisure at a slower pace, I've decided to go for a large breadth of topics at a fairly high volume and not dig too deep into any one of them. So many of the slides are going to be flash throughs. You won't necessarily be able to read everything on the slide. By the time I get to the next one, that's with intent, knowing that you can go back and review anything you'd wish to. So today what I'm going to cover are some basic resources if you're interested in pursuing more about wind engineering, definition of the wind events that we classify as hazards. A big portion of today's talk will be focusing on wind characterization. If you want to step into the realm of wind engineering and designing against winds, first thing is first, you have to understand about the wind itself. Talk a little bit about wind tunnels, a few slides on the UF and FIU NHERI facilities specifically, and also there'll be some views of some of the field studies we've done interspersed throughout the presentation. One more plug, this is the first of many, so as Matt has already said, there will be future webinars that focus more heavily on research at NHERI facility capabilities. This is more of an intro 101 type webinar. There'll also be upcoming announcements for workshops to many of these experimental facilities. You can go get a hands-on experience. And also in terms of the future, as the experimental facilities start producing data sets, they're going to be available on the Design Safe website for other researchers to utilize. So wind engineering is a fairly interdisciplinary study. You can see this is not a complete list, but I've got environmental engineering, computing, probabilistic, structural engineering, meteorology. Wind engineers do tend to think of themselves as the center of the universe, thus we're at the center. That's probably not quite true, but that's my perspective. In terms of the next couple of slides are going to give some quick resources about wind engineering in general. So there are a number of university programs that have made huge contributions to the field in the past, and some of them continue to. I won't read through the list. Again, you can review these at your leisure. I put this in here. These are consulting firms that do work not exclusively on wind engineering or hazard engineering, but they have a large component. For those of you students out there who are considering dipping into wind engineering, this slide means there are jobs waiting for you if you have an expertise in wind hazard engineering. The primary organizations in the wind engineering community are the International Association for Wind Engineering, and they have regional organizations. Here in the US, it's the American Association for Wind Engineering. Another quick plug, go to aawe.org and get your student membership. It's about $50 and plug into the community. There are major events that happen like any discipline. For example, the conferences, International Conference on Wind Engineering is every 4 years. The America's Conference on Wind Engineering is also every 4 years. And the next one is happening in about 3 weeks here in Gainesville. So feel free to explore that. We'd be happy to see you here if you want to learn more about what is on the cutting edge of wind engineering science. And of course, many of us also traverse the meteorological conferences as well. The academic journals we would primarily publish in are on that list there. This is by no means comprehensive, but if you start and work your way down the list, that's a good place to find, again, current state of the art in wind research. And also some good books as a starting point, whether it's of course you have to have the ASCE 7 minimum design loads for buildings and other structures on your desk at some point. There are a number of good wind engineering textbooks available, and also atmospheric science textbooks. We sort of run in overlapping circles quite a bit. Again, not a comprehensive list by any means. All right, so let's move into the material that covered the resources. As you see sort of highlighted text in these slides, that means that's something I'm going to talk a little bit more in depth about in upcoming slides. So in terms of the types of windstorms that would produce damaging winds, of course, we have thunderstorms, and the damaging winds come mostly from strong downbursts as well as tornadoes. There's downslope winds, which are thermally driven and require a certain kind of topography. There's extratropical storms that exist at certain latitudes, and of course, tropical cyclones. Hurricane, typhoon, cyclone, call it what you will, it's the same phenomena with different names in different parts of the world. Thunderstorms, as I said, mainly the damaging winds that come from these events are mainly from downbursts and tornadoes. And these are the primary source of wind damage in places like Argentina, South Africa, the central US, Singapore, a lot of other places. Downbursts are classified into macro bursts or microbursts. Really the only distinguishing feature is its magnitude, and therefore the magnitude of the winds at the ground level, and also the extent that it radiates out from the center of the downburst. If we take a look at a schematic of a supercell, this blue line here indicates the column of falling colder air, which would generate the downbursts you see down below. And at the trailing edge, you can also get tornadoes. So the same supercells can generate these phenomena. We're, of course, concerned as wind engineers is what's happening down near the ground level where our infrastructure is. Of course, downbursts, the reason we're concerned with them is they can do a considerable amount of damage. You consider this picture of a field of knocked over trees from downburst damage. We've all seen lots of pictures of tornadoes. This one was in Miami on May 12, 1997. Some facts on tornadoes. They typically have a fairly narrow width, but they can be up to a kilometer wide for the big ones. They usually travel less than, but can go as far as 30 miles once they're on the ground. Kansas, Oklahoma, and Florida seem to be their favorite targets. They also occur in Argentina, South Africa, India, Russia, Australia, so it is an international hazard. In the US, somewhere on the order of 300 to 1,000 tornadoes strike the US annually, with an annualized rate of 60 fatalities, $7 billion in insured losses. Every single state in the union has reported tornadoes in the past, and the tornado intensity is classified by what's now called the Enhanced Fujita Scale, which is shown here. The one that's sort of blocked out with yellow is the original or older Fujita scale. So the one we're currently using is the one on the right. And the big takeaway here is that it's essentially on a scale of 0 to 5, with 0 being the least intense and 5 being the most intense tornadoes. It's important to note that typically the way a tornado is ranked after the fact is not based on direct wind speed measurements. Sometimes they're available, but not very commonly. And so the way that an EF score is given is an estimation based on the observed damage. So there's specified degree of damage states that are applied to different building components, and experts who are trained will go and identify those damage states on certain building components and use that to put together a composite and then classify the Enhanced Fujita Scale ranking for that tornado. If there's any good news about tornadoes, it's that more than 80% of them historically have been either EF0 or EF1, or the least severe types of tornadoes. This data set, I think, here goes back over 5 decades or so. This is a map of the tornado strikes in the last several decades. Clearly, you can see that the Great Plains and Midwest are the most frequent targets, and as well as Florida. But we even get them out in California, Colorado, and every other state. This is the horizontal axis here is a 1-year calendar year. So this is just showing that the occurrence of tornadoes is most frequently during the summer months and kind of peaks in June. The total number of tornadoes that have occurred over the past 70 years or so is shown here on a yearly basis. What we're seeing here is that this is not a hazard that's going away anytime soon. The trend is fairly consistent. The annualized tornado fatalities have gone down. This is mostly attributable to early warning systems and people being more educated about what to do when there's a tornado touching down. Unfortunately, I don't think it has a lot to do with how we build structures. Most of the regions in the US that are heavily impacted by tornadoes don't necessarily build structures much better than they did 20 or 30 years ago with regard to resisting tornado winds. So another takeaway for you folks that may want to dip your toes into wind engineering, there's lives to be saved, there's problems to be solved. That means there's research to be done because it's still a structural issue that is not yet solved. Moving on to tropical cyclones, I mentioned in an earlier slide, hurricane, typhoon, tropical cyclone, cyclonic storm are all the same event. It depends on which part of the world that you're in. You've probably seen diagrams like this before that explain the basic operating principles of hurricanes. You see, you've got the eye wall, the center of circulation, and the strong damaging winds can extend dozens or even hundreds of miles from the center of the storm. Again, a busy slide that I don't expect you to read. There's a few takeaways here. This is the current Saffir-Simpson hurricane rating scale. Again, you're all familiar with the category 1, 2, 3, 4, or 5 hurricane. This recent update has removed references to accompanying surge height and central pressure to avoid confusion, and they've updated the description of the damage associated with the different categories. I want to point out, if we look here at the category 1 defined as sustained winds being 74 to 95 miles per hour, what does 74 to 95 miles per hour mean specifically? There's a big frame of reference issue that sort of beginners in the wind field have to sort of grasp before they can make headway in making heads or tails of what these intensities mean. So I'm going to be dwelling on this frame of reference question quite a bit throughout the talk. I'll take you into the field briefly to show a time trace and illustrate something. This is a map of a portion of Florida. It's basically the southeastern coast of Florida. There's Lake Okeechobee down at the bottom. This was a Hurricane Francis in 2004 impacted Florida. This is the center line of the eye wall track. And our group and others for many years have been involved in putting equipment out in the field to measure the ground level winds as the hurricane is making landfall. So this particular one with the circle around it, I'm going to show you the time trace we measured from this equipment. So a couple things to notice. Don't worry about the bottom two. Really, I'm going to focus on the top one. This is the wind speed that was measured as time goes by on the horizontal axis. Got three different traces here with different durations. So the red one, the highest one, is a 3-second gust measurement, then a 1-minute measurement, and a 10-minute measurement. So they have different magnitudes. I'll show more illustrations further. But are the maximum 3-second gusts that we measured with that tower from that hurricane happen to be 83 miles per hour. And so again, it brings up the question, is 83 miles per hour, can you copy and paste that right on the Saffir-Simpson hurricane scale? And the answer is no, not quite. So Saffir-Simpson is defined based on a maximum 1-minute average wind speed measured over open water. Whereas ASCE wind speed reference, for example, in the design wind speed maps, they use a 3-second gust over open land in what's called open exposure. By the way, a quick, very useful plug, if you go to that URL there or just Google ATC wind speed map, there is available online an interactive map where you can type in your address or your GPS coordinates and get your design wind speed for your region that's updated very frequently. So the idea is we have two different frames of reference here. We've got different terrains and different durations. So there are ways of doing these conversions back and forth. I'm not going to get into the details. There's a reference down here. But to take a Saffir-Simpson hurricane scale wind speed and translate it into what ASCE 7 calls a wind speed, you need to multiply the hurricane wind speed by 1.1. The Y I'll be talking about a little bit later. So if we do the inverse, if we take that 83 mile an hour gust and multiply it by the 1.1, in terms of how we define hurricanes, what I measured with that tower was a 75 mile an hour hurricane on the Saffir-Simpson hurricane scale. I'm putting here side by side now the enhanced Fujita scale for tornadoes and the Saffir-Simpson scale for hurricanes. You see they both now consist of 6 categories if you include tropical storms or sub-hurricane. The wind speed bands are fairly similar. That's not by any intent as far as I know. I'll note that the Saffir-Simpson hurricane scale here has been converted into 3-second wind speed gusts. But tornadoes and hurricanes affect structures in different ways, and it's not just about the speed. So a 100 mile an hour tornado and a 100 mile an hour hurricane may damage the same structure in different ways. Because, for example, the pressure distribution over the surface of the building would be different between a tornado or a hurricane, even at the same wind speed. And also the duration of the event itself. A hurricane can last hours, and a tornado for a specific structure would last a matter of seconds. There's a different time gradient with respect to how quickly the speeds ramp up and ramp back down for a particular structure. And so, again, 100 mile an hour tornado, 100 mile an hour hurricane aren't really the same thing. You wouldn't necessarily design them the same way, or shouldn't. But I'm going to move into wind characterization in 2 steps. First, I'll talk more about this frame of reference issue, and then I'll start talking about some of the ways that we statistically characterize the wind field. Starting with that frame of reference issue, when I say the wind was 100 miles per hour, it doesn't really mean much until I fill in a few blanks, such as what was the height at which I took that measurement? What was the roughness of the surrounding in the direction that the winds were approaching? So the roughness length is also known as, in ASCE 7 terms, exposure. You probably heard marine exposure, open exposure, suburban exposure. That's referring to roughness length. And there are ways of physically quantifying the upwind terrain that generates the mechanical turbulence and greatly affects the way that the turbulence and the mean wind speed behaves near the ground. The higher the roughness, the lower the mean wind speed, and the higher the turbulence is going to be riding on top of that wind speed. A third item is the duration of interest. I showed you that picture before with those 3 different traces of the same thing, giving us different wind speeds, because a 3-second gust and a 1-minute wind and a 10-minute wind decomposition of a measurement would give us different values. That third one I'll show you one more picture of. This is a trace from a different hurricane. It was originally collected at 10 hertz. And the blue line you see is what I got after I did a moving average down to 3 seconds with a peak of about 48 miles per hour or so. And then the red trace is the same original time series with a 1-minute moving average. And so we see, of course, the 1-minute moving average has a lower wind speed than the 3-second gust. And in fact, the peak occurred in different times, depending on which gust duration we were using. This roughness length I'll dwell on for a few slides. This is a way of quantifying the terrain that is upwind of the structure, because that has a lot to do with shaping how the wind interacts with the structure. And the roughness length is typically given the symbol of Z naught. There's a couple of ways of estimating what this Z naught would be. So the idea, concept, setup would be you're going to design a building and it's going to be located in a specific spot. In order to ultimately get the design wind pressures, you'd need to have this Z naught value as one of the ingredients to classify what your terrain exposure is. So one way is using these morphometric methods where you do physical measurements of the separation between different terrain obstructions and so on. This becomes very cumbersome when we translate this to the real world, where there's all sorts of different houses and trees oriented different ways and different distances apart. So for a practical reason, this isn't used very often. The way that we're attempting to popularize to get this roughness length is use statistical analysis of the measured wind traces, similar to the one that we showed you in the previous slides. There's a paper that was recently done by Forrest Masters and Peter Vickery and Fong Bacon and Rappaport in 2010, where they looked at these ASCE stations. These are automated surface observing stations that are set up at different airports and are constantly taking wind speeds. And if you determine which direction the wind was coming from, you can analyze that wind trace to get to pull out what a Z naught value might be. The question then is standardizing what the methodology should be, and that's a whole nother webinar in itself, so I won't get into the details. But it is an active area of research. The third most popular way of characterizing roughness is eyeballing it. That looks suburban to me, let's call it suburban. It's probably the most commonly used method. As I just said, there's additional research warranted to get this to a standardized way of doing things. 3 different people could visualize the approach terrain and give it 3 different Z naught scores, and that's a problem. And Z naught is a function of wind direction as well. So if behind your house is a stand of trees and in front of your house is an open field, you got 2 different Z naughts for that same location. So what's the big deal? Why is Z naught important? Why is it influential? So we're going to dig into that a little bit. Before we do, just show you a couple of pictures of what these Z naught values or exposures mean in terms of ASCE 7, for example. We've got a building that's on the coast, so if winds are coming off the ocean, this would be something that was designed using a marine exposure. On the right here, we've got exposure C, or open exposure, so buildings on land that have minor obstructions periodically, and then C is more of a denser suburban area. And again, the bottom line is the wind will behave near the ground level differently at these 3 different locations. So in addition to just exposure D, C, and B, it's not quite that simple, because the Z naught is actually a continuum where they put bounds on what we call exposure C of this Z naught value, which is typically measured in units of meters. So they call exposure C a Z naught of 0.02, exposure D is 0.005, and exposure B is 0.3, for example. But the reality is you could be in densely suburban or mildly suburban, and you get 2 different wind fields, even though you're both in exposure B. So this is a lot of meat on the bones for additional research. So let's talk about the importance of Z naught. I'll show you another result of a different deployment. This was Hurricane Ike in 2008. There were many different universities came to the field and put lots of instruments in lots of different places. So there's Texas Tech, Louisiana State, Florida International, Clemson, University of Florida, and there were others as well. I'm gonna focus you right here where I'm moving my mouse. We put up a couple of towers actually right here. You can see the path of the storm is in yellow. And I'm gonna show you some results from those 2 locations. So here's an aerial view, zoom in of that same location. And here's what's going on. We put one tower, we call it T3. in what would be open terrain. These colored swaths represent the direction the wind was coming from at that tower, so out of the east, for the time traces that I'm about to show you. And then the second tower we put on the back end of a suburban neighborhood. So these two locations from that wind direction would have very different Z0 or roughness values. And they're only less than 2 miles apart. So it's essentially the same wind field impacting both with different roughnesses in front of them. So remember that the green is the suburban exposure and the blue is the open exposure. And if we start by looking at a 1 minute average over a couple of hours of time, if I'm reading this right, we see that the open field tower is getting 1 minute averages, of 62 miles an hour or so at its peak. And behind that suburban neighborhood, they're getting at most in the mid-low 50s, and the averages are even further separated. If we look at then the 3-second gust versions of these, you see again the influence of the roughness. Now we're getting peak 3-second gusts of as high as 85 miles an hour in the open exposure tower, and then about 75 miles in the tower that's behind the suburb. So again, Z0 controls a lot in terms of how the wind behaves as it's interacting with our structures. Right. So I think I already touched on this, the frame of reference conversion. If we have height as a frame of reference, we have roughness as a frame of reference, and we have duration as a frame of reference. If you want to convert from one to the others to do an apples to apples comparison to, for example, extrapolate what you measure at one location to a different location with a different exposure, there are ways of doing conversions. In other words, if I'd only measured what I measured in the open field in the previous slide and didn't measure behind the suburb, there are ways I could extrapolate and get a decent idea of what I would have measured behind the suburb by using conversions. Well, I already told you the conversion for the Saffir-Simpson hurricane scale versus ASCE 7. It might make more sense now. The 1 minute sustained marine exposure at 10 minutes is the reference for Saffir-Simpson. A 3-second open exposure over land at 10 meters is for ASCE 7. So the conversion in this case includes both a roughness conversion from marine to open and a duration conversion from 1 minute to 3 second. And skipping the pages of derivation, that's where the 1.1 factor comes up to convert back and forth. All right. So now you have some sense of the importance of these frames of reference by what do I mean by 100 miles an hour. We can start talking about the statistical characterization of wind speeds. Again, there's a number of items on here. The red ones are the ones that I'll spend a few moments on. It's also, by the way, not a comprehensive list of ways of analyzing the wind speed, but these are perhaps the most important ones. So just jumping into the first one here, we'll talk about what's called the boundary layer profile. So the boundary layer refers to the behavior of the wind as you go further in height. So the vertical distribution of the mean and the turbulence in the wind. So in this figure, you can see what we call the boundary layer of the mean wind speed, where the vertical axis is the physical height, and down here is the origin or the ground level. So wind speed, mean wind speed gets larger as you go up until it reaches a certain height. On top of that mean wind speed, there is that turbulence. If we isolate the turbulence by itself and illustrate it like so, if we put them two together, then we have an instantaneous time snapshot of what the wind speed might be through the vertical profile. And we're going to talk about, the quantification of the mean and as well as the turbulence. So the mean wind profile, kind of focusing on that, of course, the Earth's surface retards the movement of the air. Mean wind speed increases with height. The wind field also exerts a shear stress on the Earth's surface. That's a major driving force for storm surge, for example. There are a couple of different common ways of modeling what this curve should specifically look like, whether it's parabolic law, power law, logarithmic. I'm only going to show one of these for the sake of showing it. This presentation is not going to be equation heavy, I promise you. But here's an example of the power law. What we see here is we have an anchor observation. So at a particular height, say 10 meters, we make an observation. That observation is the mean wind speed at that height. If we know what the terrain constants are, so if we're open or marine or suburban, we have different constants in this equation. And then this Z would then represent different heights other than 10 meters, and out comes your mean wind speed at those different heights. So using that methodology, we get something along these lines where these are different mean wind profiles for different terrains, right? So Here we've got the open water, then we got flat open terrain, then we get suburban and then urban or deeply suburban boundary layers. They all have a common frame of reference up at the top here. So this is just saying if your house is near the ocean or if your house is 5 miles inland, you're going to get very different mean profiles. It's not even quite that simple, because typically a building is not located in a spot where you could say that the exposure is actually suburban. It's usually a combination of things. Consider a coastal community where the wind is approaching from the left to the right. And so you've got open marine exposure, then open exposure, then suburban exposure. The boundary layer winds up being a combination of those things, depending on how long, what the distance is between these things. And so we develop what's called these internal boundary layers, where you can have fairly sharp kinks in the profile as a result of transitioning from one exposure to another. So if we now go back and refresh ourselves, we've got this snapshot of the mean wind speed and the fluctuating turbulence sitting on top of it. Let's talk more about the fluctuating component. The wind characterization, the way to characterize turbulence is what we call the turbulence intensity. It's a very simple thing. Here's a little secret for you. Turbulence intensity is just coefficient of variation. It's just the standard deviation of the measured wind speed divided by the mean wind speed. There are different components of it. This U sub V and sub W refer to the longitudinal component, the lateral component, and the vertical component. So longitudinal component would be the turbulence in the same direction that the mean wind is heading. Lateral component is perpendicular to that wind direction in the horizontal plane, and then the vertical, of course. So sometimes it's referred to as TI, sometimes it's referred to as I, but this turbulence intensity, also we want to quantify that and how it behaves as you move from ground level up to higher up. So here's, again, an example of one type of an equation, one model available to modify the turbulence intensity profile. And depending on which models and which exposures you're using, you get something that looks like this. So again, orienting you, the vertical axis is the physical height that we're doing the calculation or taking the measurement at. The horizontal axis now is just the turbulence intensity. Remember, it's just a coefficient of variation. So it's 10% turbulence, 20% turbulence, 30%, and so on. And of course, as you get closer to the ground, where those physical objects are that are creating mechanical turbulence, you'll get higher turbulence intensities than when you're higher up in the atmosphere, where the effect of the ground obstructions are less significant. So these boundary layer profiles would consist of both the mean profile and the turbulence intensity profiles. They both share dependencies on certain parameters, as I talked about the elevation above the ground. Go up higher, turbulence intensity decreases, mean wind speed increases. Terrain exposure. As your roughness increases, your turbulence intensity increases and your mean wind speed decreases. Both of these things are important to match if we get into experimental methods, say in a scaled boundary layer wind tunnel. You don't just put a model and blow air on it with a fan. It's a lot more, a lot more to it than that. One of those things that's important to match is the appropriately scaled boundary layer for the terrain in which that building you're designing is going to be set. So I'm going to move on to another major categorizer of the behavior of wind speeds called the Gust Factor. This is nothing more than the ratio of the peak wind speed observed at a certain gust duration, little t, over the mean wind speed over an entire observation period of capital T. I'll show you a picture that makes more sense of it. It's typically actually an expectation over many samples and not just one sample of a peak and a mean. The choice of what the gust duration would be, typically for wind engineering, we usually use, again, a 3-second gust to be consistent with ASCE 7. And the duration in which you seek a single gust, the capital T, is usually 10 minutes or 1 hour, depending on your purposes. So here's a plot of what's going on. Again, a wind speed trace. If we did a moving average at 3 seconds and pulled out the largest 3-second gust that we measured over this time frame, it would, let's say it's 68 miles per hour. The complete duration of this record is the capital T, that would be 5 minutes. So little t is 3 seconds, big T is 5 minutes, and the gust factor sample I have would be the ratio of those two numbers, or 1.42. That would give us a single sample of the gust factor. We'd then go into the next 5-minute duration and pull another single peak, and the next 5 minutes and get multiple samples of this ratio and then take an average. We've got an expected value gust factor. Obviously, the duration you choose has an impact on the gust factor. Right? If you look in 10 minutes worth of data instead of 5 minutes worth of data, if your capital T goes from 5 to 10 minutes, you're going to find a bigger gust in 10 minutes than 5 minutes, on average. Again, there are multiple models to quantify what this gust factor should look like. This is a plot of 3 such models. And again, it'll take some orientation here. The vertical axis is, in fact, that expected value gust factor ratio. The horizontal axis is the duration of the gust. So the 3-second gust we'd pick up vertically. The 3-second gust would be 1.5 to 1.67, depending on the model that you're using. There are several things that are frozen on this plot. For example, the things that I've boxed in on the right. This is for a 1-hour duration, capital T of 1 hour. For every single sample of the gust we got to get the expectation, we looked in 1 hour of data to pull a single gust of 3 seconds or 10 seconds or whatever. This was all done in open exposure and it was all taken at 10 meters. If I change any of those things, these plots will change. So a quick quiz to think about. Obviously, you guys can't respond to me, but see how quickly you can come up with an answer, how well you're grasping the concept. If I increase the Z0, keep everything else equal, what's going to happen to the gust factor? If I increase the height at which I'm taking the measurement, what's going to happen to the gust factor? If all the things being equal, I go from a Gaussian distributed wind speed to a positively skewed distribution of wind speed, what would happen? So quiz is over, here's the answers. The gust factor is going to increase with the density of the upwind terrain. The Z0 increases. We've already seen that before, right? The turbulence increases, the mean decreases as Z0 goes up, so your gust factor is going to go up. Gust factor is going to decrease as height increases for the opposite reason. Mean wind speed will go up and turbulence will go down as you go higher up. All other things being equal, a positively skewed wind speed would increase the gust factor because you have a heavier tail to the right and therefore higher observed gusts riding on top of that median wind speed. Moving on to the next important wind characterization parameter is the length scale. So the turbulent flow over land as the wind advects from here to there can be conceptualized as a superposition of different eddies of different sizes and speeds, bumping and moving and spinning off. I'll show you a graphic that makes that fairly clear next. And the spatial size of these different eddies is very important for design. So if we know the spatial size of these eddies, we can have some knowledge of would a typical gust envelop an entire building or just glance on a corner. Would those big gusts of wind last for 1 second or 10 seconds? This is particularly important, the coherence of the spatial component of the wind for large flexible structures. Imagine a long span bridge. We want to know have detailed information about how the wind is going to be different on one end of the bridge versus the other end of the bridge. And length scale is a way of capturing this information. So here's that graphic. Orient you again. This top one is a plan view looking down on, say, a 2,000 square foot building here. And these different colors correspond to different speeds within a wind field that's translating from right to left. So different size eddies moving and bumping and spinning off, going different speeds and so on. And the bottom one is just an elevation view of that same thing. So what I'm talking about here is finding a methodology of getting a quantification of the physical size of these gusts as they're flowing past the structure. So this is called the length scale, and more specifically, we're talking about an integral length scale. It'll become apparent why in a moment. So the eddy size is quantified by the integral length scale. There's a definition by the American Meteorological Society. It's just that red arrow I showed you, the physical dimensions. And these are, the length scales can be thought of as the mean eddy size. So going back to be clear, this methodology is not going to give us the size of this gust and this gust and this gust and this gust. It's going to mash that all together into an amalgam and come up with a typical size gust that's flowing over the location. So it's fairly straightforward. If we say that we represent the wind speed as a random variable called x, we can use expected values to get what's called the mean removed autocorrelation function. So this is the wind speed at some point in time, and that same wind speed some point forward in time, say 10 seconds or 5 seconds, represented by that top. So this is a quantification of, if you will, the memory in the process. How much does what is happening 5 seconds from now have to do with what's happening right now in terms of the wind speed? We take it one step further, and we divide this by the variance of the signal. So this now becomes non-dimensional, and it has a maximum value of 1. So we carry this scaled autocovariance function over. Here's how it works. We've got a measured wind record, like so. We use the equations in the previous slide to measure this scaled autocovariance function. And it would look something like this in the case of wind speed. It very typically looks like an exponential decaying function. So this specifically says, for example, the horizontal axis here is the lag, that tau value, and the vertical axis is the degree of correlation. So this is saying, of course, when tau is 0, the wind speed is perfectly correlated with itself at that same instant. And 10 seconds later, it still has some correlation by the time you get out to 35 seconds or so. There's not much relationship between what's happening now and 35 seconds ago. So you can imagine this is, again, a way of quantifying what I would call the memory of the wind. A big, long gust is going to have a long memory, right? It's going to be very strongly related to what's happening 50 seconds from now if it's a very long gust. And small gusts are going to have a short memory. So big, long gusts are going to have a function that looks like so. Very small gusts would be something falling in like that. So finally, if we take the integral under this blue curve down to where it passes through 0, the units of that integration will wind up being time. So looking over here, just the integration under that blue curve from 0 out to where there's a 0 first crossing is what's called the time scale. This is the time it takes for an average gust to pass the location where I'm taking the measurement. Well, if you've got the average time that it takes, and you've got the mean wind speed, you just multiply them together, and that's the average length of the gusts that are flowing past the anemometer that took that measurement. Right. Typically, near ground level, these length scales on the order of hundreds of feet. Of course, they are influenced by the height at which you're taking the measurement and the roughness of the terrain upwind of where the wind is coming from. What I showed you was the lateral length scale. Sorry, back up, longitudinal length scale. So that process I just took you through gives you this physical dimension of the average gust. But we're also interested in the lateral dimension, and we're also interested in the vertical dimension coming out of the page. Those would be much more problematic to measure experimentally. You'd need multiple anemometers, which we typically don't have. And so there have been some relationships that have been developed empirically over the years. So once you've got that longitudinal length scale, you can peg the lateral length scale to about 40 to 50% of that, and the vertical to about 30 to 40% of that. So one anemometer can do a pretty good job of capturing all three of those length scales. Wind engineering is no stranger to spectral analysis, as I suppose none of you folks are either. So this is a view of the typical energy spectrum, power spectrum of instantaneous wind speed from a measurement at a constant fixed location. So again, it looks like a decaying function here, and if you take an anemometer and stick it up and take measurements and do a spectrum, it's going to look like this. You got at the low frequency, high energy is where all those big, large eddies are, the big, giant gusts. And the low frequency, high frequency, low energy, it consists of those small eddies and the little gusts. And there's a lot of going back and forth between them as they advect near ground. Probability content is worth discussing as well. So if you think of both the fluctuating wind speed and now start thinking about the fluctuating pressure on structures that we're designing, those descriptors may differ from Gaussian in a strong way or a mild way, or not at all, depending on many parameters. Again, mean wind speed, the roughness, the type of extreme event it is, whether it's a tornado or a hurricane or a downburst, the loading location of interest on the structure, if it's on a wall or a roof. The probability content is important because it can influence, for example, the peak load assumptions behind codes and standards. And it could result in a relatively large difference in design loads on different portions of the same structure under the same wind speed. Let me illustrate that very quickly. A little mock-up of a nice rectangular plan gable end structure. Those little blue lines represent the wind separating as the wind moves from left to right, moving over the house. If we were to take a pressure measurement right at the center of the roof here, the wind speed energy would look like we saw earlier. And if I took if I did a probability model or just a histogram of the pressure I'm measuring, it might look something that's fairly Gaussian. If I just move to a different part of the same structure under the same winds, we get something that looks very different. Again, the same wind, same spectrum, but now the pressure that's acting at that location on the same structure looks very different. So the extreme uplift that is experienced in this portion of the roof is going to be different from the uplift in that portion, in the other portion of the roof. So capturing the probabilistic content is, of course, an important part of characterizing wind structure interaction. Okay, now we'll talk about the best friend and worst enemy of wind engineers, which is the pressure coefficient. This is a dimensionless parameter. I like to call it a filter that relates the wind speed that approaches a structure to the pressure experienced by that structure. So it's usually referred to as CP. The ingredients here in the numerator, little p by itself, is the dynamic pressure that you're measuring at a given location. For example, those previous two spots, the green and the red, will be measuring little p as a time history. P naught is a reference pressure that isn't changing as a function of the wind. So this could be barometric pressure. It could be the pressure 40 meters above the structure. It's something that's not being influenced by the structure itself. And then rho is air density, and then V is wind speed. Again, here it comes. What do you mean by wind speed? What's your frame of reference? Is that a 3-second gust? Is it a 1-minute gust? Ultimately, the purpose of this equation is to invert it. Right? We're going to have CP from wind tunnel tests. And the way that we use the equation is solve for the pressure by taking the pressure coefficient for that structure, that part of the structure, and multiplying it by wind speed. Well, if the CP was measured in a wind tunnel using a 3-second gust wind speed reference, and you wind up multiplying it by a 1-minute wind speed, you're not getting anything that means anything, right? So again, every time you see velocity, think, what is its frame of reference? And different frames of reference are appropriate for different applications. So in the vein of what I've just said, if we have a wind tunnel pressure tap that is measuring the fluctuating pressure on a given spot, we could get a time history of that. We put that time history through this equation, we would then have a time history of this fluctuating pressure coefficient. Maybe it looks something like this. And so there are different types of pressure coefficients depending on what your purpose is. Of course, you could have the mean pressure coefficient. You could get the fluctuating or RMS coefficient, or the spread of that fluctuation. We're also very interested from a design standpoint for the peak pressure coefficient. Typically, it's illustrated here as this single point here, but in reality, would do extreme value analysis on a long time history to quantify a peak. Because it's up to you to say, should peak represent a 5% probability of exceedance, or what? And where there's a peak, there's also a minimum. All right, so here's the trick with pressure coefficients. The measured pressure and, of course, the pressure coefficient are going to differ over different surfaces of the same building. I illustrated that a little bit earlier. And they're also going to differ as the wind direction changes. So in these illustrations here, if the wind is coming from left to right, you see this red illustrates what the pressure might be in different portions of the roof. The pressure coefficients I would measure in this portion of the roof and this portion of the roof, and the wall up here and down here and the backside will all be different. So then if I take what the measured pressure and translate it and simplify it into nice uniform distributed loads, the resulting loading over the surface of that structure when the wind's coming left to right might look like we're seeing here in this right figure. However, if I change the wind direction, that whole picture is going to change, right? Just think of the mirror image. This is going to flip over here, that's going to flip over there, and so on. And if the wind is heading into the page, it's going to be different still. So how do I quantify what is the pressure coefficient for any given spot on that building? The answer is, for design purposes, we do what's called take an envelope. So for any given spot, we would put a model in a wind tunnel and run it around all 360 degrees, put it on a rotating turntable. And for any given location, we just take the pressure coefficient at its worst. So at the worst pressure coefficient from any direction measured every spot on the building is what then becomes the pressure coefficients that are assigned to that building. And here's what we do with it. So warning in advance, this is essentially an attempt to do a one-slide explanation of ASCE design pressure, which is a dangerous thing to do. So I'm keeping it simplistic, not quite accurate for a reason. So ultimately, we want design pressure. When building a building, what pressure do we have to design it to? So if we take our 1/2 times air density times the pressure coefficient times V squared, this is the inversion of the pressure coefficient that I talked about previously. Then you've got 4 more coefficients in here that are modifiers for various things. So the KZ is a modifier, a coefficient modifier. KZ contains the information about Z naught. If you're in exposure D or C or B, if you're in marine or open or suburban exposure, that's going to be a modifier that changes your design pressure depending on the surroundings of your building. There's also a factor for topography. If your building is sitting on top of a hill or an escarpment, you'd have a factor there to change your design pressures. There's a directionality factor. This tries to back out some of the enveloping I talked about in the previous slide. So it's unlikely that when your building does see its design level event, it's going to happen to come from the worst case direction for that house, and so there's a reduction factor allowed for that. There's a gust effect factor that is a very different animal depending on if you're a flexible or a rigid structure that's being designed. And there's the pressure coefficient we talked about and the design wind speed. Of course, we'd be using ASCE 7 maps to get this design wind speed. That's going to be different depending on where you're located and in the country. Wind speed maps have contours with wind speeds on them. And you're going to use different maps depending on what the purpose of your structure is. If it's a hospital, the wind speed maps look different than if it's a barn, for obvious reasons. The controlling the level of conservatism. Okay, so now I want to move into some sort of research ideas. The idea, hopefully so far, I've whet your appetite a little bit or informed you a little bit about the basics of defining the wind hazard and how we statistically quantify it. So things that I and others have been working on recently and going way back for decades include the following non-comprehensive list. Right, we've been following in the path of the earthquake folks for a while, developing fragility models for common building components as a function of wind pressure and debris damage and so on. The name of the game here in terms of resilience is cost-effective mitigation for prescriptive and engineered systems. That means changes in building codes. For example, in Florida, the Florida building code is fairly progressive about how they dictate how structures are built. And also mitigating older structures, right? No matter how much you change the code, there's still the issue of all those structures that were built beforehand. And on paper, it's easy to design a structure to be essentially wind impervious if you're willing to spend the money, right? So it's all about the engineering. How can I make that house survive a category 3 instead of a category 1 and not drive the cost of building that house up by a factor of 2, right? That's the long and the short of it. And a big list of other topics here that are worth considering. To motivate you, if you know nothing about wind engineering except what you heard today, you saw that earlier slide, all the different contributors to the field of wind engineering. If you have experience in or any interest in the following fields, which is a non-comprehensive list, we need fluid mechanics people, computational fluid mechanics, thermodynamics people, stochastic modelers, structural designers, people who focus on sustainable materials, environmental engineering, natural ventilation, remote sensing and instrumentation, meteorology, coastal processes. Cheryl N. Blaine, I'm talking to you. Then, of course, you're all there's a spot for you at the wind engineering table for sure. I'll talk very briefly about some investigative tools and research infrastructure to support those research concepts I had on the previous slide and others. So boundary layer wind tunnels, something I've mentioned a couple times, but I haven't showed you one. These can be scale model wind tunnels. For example, UF has a boundary layer wind tunnel as part of the NHERI facility, and there are other facilities around the country. There's full-scale versions of this. For example, Florida International has the Wall of Wind, or the WOW, which is essentially a full-scale version of a wind tunnel. But both of those facilities have different and complementary functions. I'll talk a little bit about pressure loading actuators, which are a way of importing pressure loads dynamically to building systems without actually putting them in wind flow. This is based on Greg Kopp and the University of Western Ontario's Three Little Pigs project. It helps us to investigate load paths, failure load mechanisms, and so on. And I've already showed you some snapshots of the field investigations of measuring ground level hurricane winds. There's also a lot to be done in terms of post-storm investigation. In fact, that's one of the entities of NHERI, is the RAPID facility, is to get resources and expertise to help you to go into the field after an event and start collecting the critical information before it perishes. It's worth noting the one good example of what to do with all this ground level data we've collected, what I call this horse's mouth data, is when we're going to set up a wind tunnel and calibrate it and commission it, we've got hundreds and hundreds of hours of collected field data from real ground level hurricane winds to use as statistical targets, right? And that's a big benefit. So just spend a few minutes more of your time. This is a view of the University of Florida's boundary layer wind tunnel. It is part of the NHERI facility. I'll walk through a schematic of it in a second. In most respects, it's very much a traditional concept boundary layer wind tunnel. Diagrammed like so. We've got the wind moving from left to right, in this case, powered by a bank of fans. You got a screen of honeycomb that straightens out the vorticity in the air particles that it picks up by going through the fans. Goes past some Irwin spars to start trying to build up some of those long length scale eddies into the wind field. Then it goes over the roughness element grid. So this is what is going to control the boundary layer by the time it gets to the turntable where our model that we're testing to measure wind loads is going to sit. So this is a picture of not our wind tunnel, but a different wind tunnel. So I want you to focus on what's called the roughness elements. In the previous one, the roughness elements are here. In this one, the roughness elements are here. These are static elements, right? These particular roughness elements would be set up to produce, say, a suburban boundary layer for this house test model here. If you wanted to then run a test on this same model for an open terrain, you'd have to stop, take away all these blocks, put in new sets of blocks, recalibrate, and start again. Most commercial and even research facilities have pre-calibrated, but the idea is it's a very labor-intensive process to move from one terrain to another, or a different scale to another. If this is a 1/50th scale model and I wanted to move to a 1 to 100 scale model, again, I'd have to change all those blocks. So the cool feature about, the unique feature, and I think it's a cool feature about the UF wind tunnel, is the so-called Terraformer. So this is our roughness element grid, and every single one of these are individually controlled with stepper motors. So each one of these can go anywhere from 0 to, I believe it's 8 inches tall individually. They don't have to all be set to the same level. And they've got a broadside and a narrow side perspective as well. I'll show you very quickly. I'm going to skip forward. You get the idea. This is us setting up running the Terraformer to achieve a certain terrain profile. Don't mean to make anyone car sick here. Right. So what's the benefit of that, is the following. Since we've calibrated and automated exactly which orientations of those blocks give us which boundary layers and at which scales, we can seamlessly move in a matter of minutes from marine to open to suburban, from 1 to 100 scale to 1 to 50 to 1 to 400. And what could take weeks or months of setup at a traditional facility, we can do in a matter of days, assuming nothing else goes wrong. So the traditional facility will be able to give you different exposures. It'll give you that exposure, that exposure, that exposure. Our facility can put you anywhere on this continuum in about 2 minutes time. And a different look at it in terms of different scales, again, to 1 to 400 scale models, 1 to 40 scale models, roughness length on the bottom here, so very open to very deeply suburban. We can generate the appropriate boundary layer anywhere in this envelope in a matter of moments. And there's a few things coming up in the future. I won't dwell on these, but we're also going to add some more control to the mean wind speed to get a non-monotonically increasing boundary layer for things like, to simulate things like downbursts. And an eye profiler to get more control over the turbulence intensity to give you perhaps non-homogeneous, non-stationary turbulence in the wind field. And that's going to open the door to more research areas than we can achieve right now in any traditional facility. One slide on pressure loading actuators. As you can see the scale here by the person standing here, this is another facility at University of Florida. This is basically a giant pressure box. This is a wall system that's put inside that pressure box. And we can put positive and negative pressure on this, not in a static way, but in a very dynamic way. So imagine building a scale model of the building this wall belongs to, going into the wind tunnel, getting a dynamic trace of pressure, scaling that pressure up, and then playing it back on the real thing to see where its failure mechanisms are going to be. That's one example of the dual use of the facility. All right. Also want to talk about Florida International's Wall of Wind facility, which I've touched on before. So this is a much bigger version of the boundary layer wind tunnel that I showed you earlier. They don't have the actuated terraformer, but it's not necessary for what they do. So this is the back end. The wind is going in. You can see the scale from the gentleman standing here. And on the front end, the business end right here, we've got a model that is can be a much larger scale model than we can achieve in the University of Florida's boundary layer wind tunnel. This place is, so you can do the kind of things here, for example, destructive testing and aerodynamics and wind-driven rain and so on larger structural models or even full-scale models than you can in a traditional wind tunnel. This place is really cool. I really strongly advise you to visit Florida International University's Wall of Wind facility. And in fact, you've got an opportunity coming up right around the corner. So here's a quick plug for a NHERI facility. The Wall of Wind is hosting a workshop June 15th to 16th, 2017. I'm not going to read through all of this, but the idea is to bring in people who may be interested in writing proposals to NSF to utilize the FIU's Wall of Wind to get to know the ins and outs and get to know the researchers and to learn more about wind engineering. You can go to the Design Safe website to figure out how to register for this and attend. So please take advantage of that if at all possible. UF is going to also have a workshop coming up. The date hasn't been set, but it's going to be later this same summer, and you'll be notified through Design Safe when that's available. So this is my last slide. I'm just reminding you, more webinars are going to be coming up, more workshop announcements. Data is going to be going on to the CI. And remember that website, and thank you very much for your attention.
Thank you very much, Professor Gurley, for this background information. It was very informative, and I had no idea that wind engineers were at the center of everything. So that background was very useful to know.
Just ask.
In seriousness, I think it highlights the complexity of the field measurements and the complexity with characterizing the hazard in a simplified way that can be meaningful for design. So thank you very much for this information. And we're going to start the question and answer session. I'm going to remind the attendees that you remain in a listen-only mode. And so if you have a question, please relay those through the chat function. And so the first question comes from Dan, who's curious to know what can homeowners do when working with a contractor to make sure their home is rated for a tornado strike? And the follow-up is, are there any current products available for new construction or retrofit that we should be pointing people to? Okay, so I'm sorry, I'm gonna ask you for the second part again in a moment, because I was thinking of the answer to the first part while you were talking. So, Dan, the thing to remember is that there's a FEMA report, I believe it's FEMA 350, that is an official guideline on how to build a safe room, a tornado shelter in your house. So you're not going to build a house that is tornado proof. The thing to do from a cost-effective standpoint is to build an interior room in your house that is fortified against hurricane loads. And there's a number of features, specific engineering features that would go into accomplishing that. I can tell you, I just had, 2 years ago, I built a house in Gainesville where I am now. I sat down with the contractor and I said, I don't want FEMA 350 by the letter because it'll be very expensive, but I want this room to be fortified for tornadoes. And he knew exactly what I was talking about, and we worked it out. I believe I wound up spending an extra $1,500 to make it fortified to my satisfaction. It's not FEMA 350 compliant, so be warned about that, and I don't claim it to be. I'll also say, when I had built an earlier house in Gainesville many years ago, sometimes when you sit down with the builder and just let them know that you know something about residential construction to resist hurricane winds, things get changed behind your back. I had meetings with my contractors one day, and it was the first, the framing was already up and they'd already put in the roof to wall connections and everything was up to code. The next meeting, I just happened to mention that what I do for a living. I came back next week and they'd swapped out all the roof connectors for the strongest thing you can buy on the market without me ever saying a word or even implying they should do so. So don't be surprised if contractors have, a bit of knowledge about how to fortify. You just have to be knowledgeable enough to ask what can be done and be aware that there's, every mitigation measure has a certain price point. The primary thing you need to do for, well, I'm going to take that back. I was going to say window protection, but that's more of a hurricane thing than a tornado thing. And Matt, can I ask you to repeat the second part of the question? Yeah, the second part was, are there current products available for new construction or for retrofit that should be we should be pointing people to? Making people use? Or suggesting their use, yeah. Oh, yeah, sure. So I was about to say, so we can design, there's a problem of sort of a, what I call the Superman complex and the damsel in distress complex. So a hurricane makes landfall in a part of Florida. National Hurricane Center says it's a Category 3 storm. A person who lives in a house 80 miles away barely experiences tropical storm force winds. And they say, I survived a Category 3 storm. My house was built in 1980. Everything's fine. I don't need to do anything. That's one problem, is getting people to better understand what the actual risks are. There are simple things you can do. Say, for example, hurricanes, protecting your windows is one of the most important things you can do. Not just because windows cost money to replace, but because when the wind gets in and changes the internal pressure, all things can go to heck fairly quickly. It also lets in a lot of water. You get a lot more content damage. So window protection is very important, whether it's fancy metal shutters or putting wood paneling. A modern roof shingle. So roofs are supposed to get re-roofed. Shingle roofs are supposed to get redone every 20 years or so. Make sure when you get your roof redone, it's done with the highest rated shingles that you're willing to afford, because they're much more wind resistant. Once the shingles start going, that's how the water gets in. That's how the damage starts building up. There are some
modifications that have come into building codes in a direct response to making them more fortified. So this is a nice way of, the future structures being more resistant. So the Florida Building Code, for example, is fairly progressive about taking the outcomes of research and trying to integrate them into the codes and standards. So homes built in the 1970s in Florida are very different than the way they're built now by law, by code, specifically making them much more wind resistant. So that's a long answer. The short answer is yes, there are many things one can do to existing homes and also planning for new homes that would definitely make them more resistant to hurricane and tornadic wind loads.
Okay, and the next question comes from Cheryl Ann, and her question is, for hurricane wind situations, how do you separate wind versus surge-induced damage?
Oh, Cheryl Ann, that's a good question. After Hurricane Katrina, so I'm assuming you're talking about a forensic analysis of a house that has been damaged and maybe experienced some surge and some wind. How easy it is to separate depends a lot on the relative severity of them. So typically speaking, as wind speed gets faster and faster at a given house as a hurricane is exposed, the house is most usually going to start suffering its damage beginning at the roof and working its way down. So houses that are mildly damaged might have a few shingles missing. A little more wind speed and you maybe get some more shingles and maybe a window's broken, maybe a piece of plywood decking comes off. By the time you get to structural wall damage, you've got a very weak house and or a very, very strong wind. Surge damage typically is from the ground up. And I mean, typically means if it swallows the whole house, who knows, the house is usually gone in a surge zone after coast of Mississippi after Hurricane Katrina. So if you look at a house that's still standing and it has experienced surge and wind, you can get a sense of how much damage the wind did by looking at the roof. If the roof is intact in good shape, chances are the wind speed didn't really get high enough to do significant damage. Whereas if the facade is damaged 3 feet down, water did it. Fairly straightforward. Now, which one broke which windows and which one got there first, that's a whole nother apple to peel, and not such an easy thing to answer. I would rely a lot on modelers like yourself, Cheryl Ann, to give me information on the relative timing of the intensity of the hazard at that location, being surge versus wind.
Another question has to do with the ramping up of tornadoes and hurricanes. Can you elaborate on how long it takes for these storms to ramp up?
But are you talking about the time gradient of wind speeds building up due to an approaching hurricane versus an approaching tornado?
I would think that's the question, yes.
Okay. So tornadoes are very, scale-wise are much, much smaller than a hurricane. It may be a reason it gets less attention in the building codes than hurricanes, because even when a tornado does make landfall, and as we've seen in recent years, it can do a lot of damage very quickly and kill people. But the likelihood of any one structure being struck is fairly small, right? But as a tornado traverses and makes its way towards a house, the house might not experience significant damaging winds from a tornado until the tornado is within several hundred feet of the house. And so all of a sudden it goes from 30-mile-an-hour gusts to over 100 miles an hour in a matter of seconds. And that can, the rate of that change can have a lot to do with how the house is damaged. For example, the internal pressure drops around a tornado, and if the interior of your house is still pressurized from regular atmospheric pressure and there's a sudden drop in exterior pressure, that can affect how your walls and windows respond. A hurricane then is really dependent a lot on the translation speed of the hurricane. So that we're talking about, Francis, the one I showed you a plot of earlier, took a matter of days to move its way over the coast of Florida. It was very slow moving. So when we were deploying, we would be in gusty 30, 40-mile-an-hour winds for 24, 48 hours before it ever got up to 100-mile-an-hour winds, or a little bit less than that actually in that storm. So there can be very drastic differences in the ramp up of the wind speed between those two different events.
Okay, and I think we just have time for one last question, and this one has to do with the NHERI equipment facility. And the question is, what kinds of projects are you looking for at the facility?
Oh, okay. Well, essentially we want the same kind of projects that NSF wants. That is to say, transformative and impactful. The project, and specifically projects that can maybe harness the unique features of, for example, the boundary layer wind tunnel. We don't want projects that could easily be done at other boundary layer wind tunnels. So I'll give you two examples. Example one, you propose a project, you're building a house and you want to know what the wind loads are on your house. That's not transformative or impactful in any way. It could certainly be done. It's not something NSF would fund us, I'll tell you that much for sure. If you instead wanted to investigate, say, the feasibility of a building with actuated components that respond in real time to mitigate wind and improve its performance, and we could somehow replicate that actuation in the wind tunnel, now we're talking about something that hasn't really been done before, and something that could be very impactful and transformative, not just for wind engineering, but perhaps also the technology, instrumentation that how it would have to be developed for that. So I can't give you a too much clearer answer than that, but something that is going to take a chance and do something that hasn't been done, and something that would be hard to do any other place but our facility. I'm fairly certain Orendum at FIU would say the same thing about his facility. The best way to find out if your idea is a good seed of an idea for us or not is just to get in direct contact with me or the other co-PIs from my facility, and we'll talk you through it. We'll help you with ideas. We'll help you co-develop proposals, give you all the information you need about budgeting and so on.
Excellent. Thank you very much. So we're at the conclusion of today's Natural Hazards Engineering 101 seminar. On behalf of everyone in attendance, thank you, Professor Gurley, for taking the time to join us today. To those of you in attendance, thank you for your participation and your questions. We have some more exciting webinars coming up on Natural Hazards Engineering 101, as well as research highlights, and these can be found at the website, which is currently linked on the screen on Professor Gurley's slide. So thank you very much for your attendance and participation.